We have our talk now. This rated really well in the review process, and I'm really looking forward to it as well. Don't look aside or you'll miss it, turning a Hyper-V cache miss into 200K of cash. Leo Adrian, let's welcome him to the stage.
Cool. Hi, everyone. Thanks for coming. Hi, I'm Leo. I used to be a pen tester, but for the last year or so, I've been an independent researcher focusing on Windows. And a shout out to the Missing Link team, because I started there less than 5 years ago, and now I'm standing here finding O-Days. So yeah, great team over there. Cool. So this talk is a little bit of a journey. Definitely a bit more winding and precarious than I thought it would be from the start. It follows the tale of some cool research I did back at the very end of last year and through January. And as I mentioned, I'm an independent security researcher. So my goal was I wanted to find a really cool or really good Hyper-V bug, earn some bounty money, and that would set me up for the rest of the year to do some other research that was maybe less profitable. But like all good research, it took a bit more of a circuitous path than I was expecting. And so hopefully, by sharing that with you today, I can remind everyone you don't have to be an ultra-elite hacker who started when you were 5 years old. You can also just be someone who's very persistent, not afraid to try something new, and make lots of mistakes along the way. And I saw this tweet the other day, like 3 days ago, I think, and I just had to put it in here because this is exactly what it's like. Yeah, you have this amazing goal in mind, and nothing goes quite the way you expect. So Hyper-V, what is it? Hyper-V is Microsoft's virtualization solution. So it's what they use to run VMs. So both in terms of the Azure cloud, if you spin up a VM there, that's running on top of Hyper-V. But also if you've just got a Windows 10, Windows 11 laptop, you want to run some VMs, Hyper-V comes by default. You do have to, it's free. You do have to install it, but you don't need to pay anything extra. It's just kind of there alongside the operating system. And it also is used for some security features. We're not going to talk about that, but like secure isolation mode for LSAS, stuff like that. But what does a virtualization platform actually look like? There's a lot of components. It's pretty complicated. You definitely don't have to remember all of this. But there's sort of three main components to Hyper-V. There's what they call a root partition. This is just your host operating system. So technically, when you turn on Windows 11 with Hyper-V installed, that's actually like a VM that you're seeing with your desktop. It's just a very special one they call the root partition. Partition's the Windows term for VM. I'll probably just use them interchangeably, but they mean the same thing. Then you've got child partitions. This is just VMs. Like if you spin up a Linux VM on Windows with Hyper-V, that's a child partition. And then underneath them all is this thing called the hypervisor, and that kind of ties them together. It does some really cool low-level magic. That's not actually what we're going to be talking about attacking today. We're looking at the root partition. But that's kind of like the overall thing. And I think legally, if you talk about Hyper-V, everyone has to include this diagram, because every talk I've seen so far about Hyper-V has it. So thanks, Microsoft. So now we have some idea what it is. What are the security properties? Why would we care about it as attackers? Well, Hyper-V, the hypervisor and sort of the root partition that manages things, they broker all the interaction between VMs and the hardware. So if you spin up a VM and you're like, I want to give that thing 2 CPUs and 4 gig of RAM, but my laptop's got 12 CPUs and 16 gig of RAM, well, Hyper-V's got mechanisms in there to make sure that the guest VM only sees the things you want it to see in terms of hardware. And also, if you've got several VMs running, like you would in a cloud, it also brokers the devices and the hardware so that the VMs can't interact with each other when they shouldn't. They can't see any other systems running on there. But as we just saw, it's a pretty large and complex looking thing, right? So when we're thinking about security, we're also thinking there's probably going to be some bugs in there. And Microsoft knows all this too, right? So they offer a pretty nice amount of money if you're able to find something that even looks like a guest-to-host escape. So it's $250,000 US if you actually have one with an exploit. But even if you don't write the exploit part of it, even if you've just got a bug that looks like it could be exploitable, they'll pay up to $200,000. And even before I'd started this research, there were other researchers who'd publicly said, yeah, they gave me the money. So that's kind of why I chose this bounty program to put some time into. So I'm not going to cover all the components here, but I sort of broke it down into like what the attack surfaces of Hyper-V are, the kind of functionality you can interact with from the guest. We're going to really focus on that root partition kernel. So that's the kernel drivers running in the host OS that you're using to manage all the VMs. But there's a lot of attack surface in the user land, so in sort of the actual processes, not in the kernel stuff. And then the hypervisor itself is also a really cool and complex attack surface, but not something I've dived into directly. So most specifically, I want to talk about this thing called VMBus. VMBus is what they call a para-virtualization framework. So normally when you have a virtual machine, right, it's an operating system. You boot it up and it goes, oh, cool, I'm running, right? I'm alive. I want to talk to some hardware, like what's my CPU? How much RAM have I got? Are there devices available to me, like hard drives, graphics cards, like network cards, things like that. And so back in the day, what they would do is they would emulate these devices, right? You would write some software that pretended to be a hard drive, like a spinning platter disk drive, really, really complex to do, really finicky. If you get it wrong, the operating system's going, whoa, the hard drive stopped working, like it's freaking out. And it's also really inefficient. So over time, they developed this better idea called para-virtualization, where you install some special drivers into the VM and onto the host that's running it. And these drivers are kind of aware that they're being virtualized, right? So you turn on the VM and it goes, oh, hey, I'm running inside Hyper-V. So instead of just acting like I'm talking to a real hard disk, I'm going to use this special set of drivers specifically for Hyper-V. They're tuned to be way more efficient and to be able to talk to the host in a way where we sort of both sides know that we're not really using hardware. We're kind of in this software abstraction. And VMBus supports a few different device types. We're going to look at storage mostly today. It does require hardware support, so if you have an incredibly old CPU that doesn't have support for the virtualization extensions, you can't do this stuff, but we're talking like more than a decade old at this point. So the fundamental technology that VMBus is built on, and that makes it really efficient compared to some of the emulation techniques, is the idea of shared memory. So if you've ever used like shared memory mappings in Windows or Linux programming, the idea is essentially that you've got your physical memory, so like your RAM, and we do some cool stuff with virtual memory and page table mappings to map the same bit of RAM into sort of the root partition into the host's memory and into the guest VM. So the addresses, like the little numbers, the hex numbers you'll see would be completely different, but actually when the CPU does its tricks to resolve the page tables, they're pointing to the same place. So this means one side can just write to a piece of memory and the other side sees it pretty much instantaneously. So it's a really, really efficient way of communicating, and that's kind of the high-level idea of how VMBus becomes really efficient is any communication of sort of mass data is just done by setting up one of these shared buffers, and what will happen is the guest will like say, hey, I've got this buffer at physical address 123, and it'll send it through the hypervisor to the host, and the host will go to the hypervisor and say, hey, the guest has sent me 123. That's not a real address. Can you tell me what the real address is? And the hypervisor will do some magic and go, sure, the real address is actually 456. And so the host can map that address, and now they're looking at the same thing. And yeah, really efficient. And if you want to think about it in kind of like an OSI model way, yeah, so VMBus kind of replaces like your physical layer, and on top of that, each device has its own specific protocol. So who've got vStore and NBSP, they're really small. We don't really worry too much about those. And then on top of that, you have your more generic protocols that you might be familiar with, like SCSI. RNDIS is like a Microsoft-specific networking over USB protocol that they just sort of crowbarred in there. But then on top of that is TCP/IP, and you have your applications above that. So it's kind of how you can think about it. And the lower level protocols encapsulate the higher ones, right? So as you're passing these, you unwrap the lower layers and pass them up the stack. And before I go any further, I want to give a shout out to this guy, Peter Hlaverty, because his blog post here is kind of what gave me the impetus for the research we're going to talk about today. I had previously looked at some Hyper-V stuff, but this was kind of what got me back into it and going, hey, like this is something I want to look at again. So this describes some very successful research he'd done. He found like 10, 12 bugs over a couple of years in Hyper-V. And he goes through his methodology here. And essentially, at a high level, his idea was like, he's going to do fuzzing, but instead of just doing data fuzzing, like, hey, I'm sending a message from A to B, and I'm going to mutate the message. He said it was to fuzz the state of the hypervisor. So it's not that the individual messages are being messed with, but like sending messages in a weird order or across multiple threads, trying to find race conditions. And like this kind of stateful fuzzing, something that's been done before with things like syscaller, but I'd never seen it talked about in the context of Hyper-V. It was really successful for him, and so I was kind of like, this is cool. Like I have some maybe ideas of where I could take this and do this kind of stuff myself. Cool, yeah, so now to get into something a bit more specific. So after reading this blog, I sort of had like a bit of inspiration, a bit of a plan, and I was like, okay, I'm going to replicate Peter's work on this sort of stateful fuzzing, but I'm going to focus on the virtual storage layer because it wasn't something I'd sort of looked at before. I was like, I've got this great idea, I'm going to implement a multi-threaded generative fuzzer written in Rust. Like I didn't have AI back then, but I probably crowbar some AI in now, right? Like really cutting edge stuff. It's going to be awesome. And so I spent some time reverse engineering this storage stack, trying to like, okay, figure out what are the different components, what are the actual drivers I'm working with. I learned a lot about SCSI. It turns out like that's just your generic storage protocol. But yeah, there's actually like some SCSI commands that are in there, but they're not documented unless you're like the member of like a secretive industry group. It's like, I guess it's like the secret to fast copying is not something they can give away for free. And I wrote like a little harness using the Linux kernel. So the nice thing about Hyper-V is all the sort of guest VM stuff for the Linux kernel is completely open source. Microsoft have upstreamed it into the Linux kernel because obviously they want Linux to work really well in Azure. And so I was able to go in there and play with that code a bit and use it to start sending messages directly through this VMBus thing into the virtual storage layer that I kind of wanted to fuzz and target. It's like, yeah, cool, things are going well. This seems like a great idea. And then I get into the fuzz and I'm like, fuzzing is awesome. Like fuzzing's really cool right now. It's in Rust as well. I love Rust. So I spent quite a while like writing this generative fuzzer. And what I mean by generative is, again, we're not mutating some particular like data or packet. Instead, we're generating packets that should be valid, but we're sending them in maybe a weird order, or we're sending them across a couple of different threads at the same time and hoping to trigger a race condition. And this was going to happen like in a Linux VM, and we're sending it down to the Hyper-V host and the kernel. And so this is basically me at this point. I'm like, yeah, cool, like great idea. I'm definitely going to find like 1,000 bugs with this thing. It's crazy fast. Like I'm doing a lot of benchmarking on it, but I'm not really doing the fuzzing while I develop it. You know, I'm like having to recompile the Linux kernel constantly is really slow. So what I do is I sort of write some stubs to be like, yeah, I can definitely send messages from the kernel to the host. But I'm going to do most of this stuff just by like writing some Rust and have it output to standard out or write to a file. Like, you know, that's kind of what I'm doing when I'm developing this thing. And it's crazy fast, right? Like I'm getting great results. It's looking awesome. So I want to just have a quick interlude and refer to Markdown's 2022 OffensiveCon keynote, where he's talking about the helpfulness or unhelpfulness of writing tooling as part of the vuln research process. So I'm going to quote him. I've seen a lot of times in my career, people start doing vulnerability research and they're like, I'm just going to automate this thing. And they spend forever doing that and they forget why they were even doing it. And they make this huge complex program that might not even be particularly useful in real life because they're things they think are elegant and are going to work in their mind, don't actually work in practice. Yeah, so I've spent probably a good month writing this cool fuzzer in Rust, and it's so fast. And I eventually like plugged the pieces together. I'm like, cool, I connected up to my little Linux kernel harness to like start sending packets down to the host, get some crashes, get a crash. But for those of you who haven't seen this particular kind of message before, this is the message you get when you make the Linux kernel really upset. And so basically, it was pretty immediately obvious that actually I hadn't thought about a bunch of stuff, and all I was doing was crashing my own guest kernel. I had this amazing idea of like, yeah, this is going to work really well. It's going to be so fast. But fundamentally, I'd failed to understand some of the protocols and technologies in use in my sort of keenness to start this project. And my attempt to just crowbar a fuzzer into this Linux kernel stuff wasn't working. Yeah, so all I've managed to do is create a buggy guest VM. It sounds like you could probably still get a CVE for it these days, but not what I'm trying to do. And in all honesty, I felt a bit silly, right? Like I'd spent a bit of time, I got really tunnel visioned into this idea of writing this particular fuzzer. But I didn't give up, and I started to like figure out, okay, what's going wrong? And it turned out that you know, there's this VMBus layer that I briefly touched on that's kind of the transport mechanism, and I hadn't really thought about that at all. I was like, I'm going to generate all this data and just send it. And it's like, okay, but like, how is it sent? And is there like a queue, and there's some ring buffers, and there's actually like, you know, there's a threshold beyond which it can't send more data and you have to wait for it to catch up. And essentially I was just overflowing all of these things on the Linux side, and then the kernel couldn't do any storage, like any disk I/O, and it was getting upset and it was crashing. So like I slowly started to figure out like, oh, okay, actually just like trying to make things as fast as possible in this case is not going to work. But a couple of days into this mess, I'm just, you know, constantly testing the fuzzer, like maybe it'll magically work this time. And actually, I suddenly get a crash, right? This is a real one. This is a windy bug, a screenshot of windy bug. So this is a crash I got in the actual host kernel. I'm like, wow, okay, we're back on. Like we have got a real guest to host crash. But like, where this came out of nowhere, like what? I thought my fuzzer wasn't working. So this way I drop everything else around the fuzzer, like, yeah, I'm not working on that thing anymore, and try to triage this crash and figure it out. So this is a stack trace. Sorry, it's probably a little bit small, but the first thing that jumps out at me, so there's the crashing instruction. Everything above that is like the Windows crash handler. We don't care about that at all. But looking at that instruction and the function and the driver that's involved and what's below it, is actually no storage stuff there at all. So this doesn't involve any part of the host storage stack. It's not in the like SCSI passing or anything. Instead, it's in this VMBus layer that I had completely ignored and not bothered to understand. And so I don't really have any background for or context for what's going on here. So I spend, luckily in like the first sort of 30 minutes, I'm able to get a very pinpoint understanding of oh, okay, this is a use after free bug. There's like a linked list being iterated, and one of the nodes in the list has been freed, and I sort of get a very rough idea of what's going on. But I don't really have any context for what this VMB KMCLR driver is or what it's doing. So I have a little bit of information about this crash, but really, if I want to report it to Microsoft and certainly get the full bounty, I need to be able to reproduce it. Unfortunately, as previously discussed, my highly advanced Rust-based fuzzer does not help. It's basically non-deterministic because of the really buggy stuff it's doing on the Linux side. So I run it a few more times. It just crashes the guest kernel. It's not helpful. I've basically fluked my way into this cool guest-to-host crash. But if I want to reproduce it, I'm actually going to have to understand what's going on and somehow manually trigger the conditions for this thing to happen again. So yeah, definitely not a deterministic fuzzer, which is a problem. But one thing I find that's really helpful is to start to document assumptions with this stuff. Okay, well, how does this actually work? What's going on? And so starting at a really simple level, the guest is sending some data, some stuff's happening, and then the host is crashing, right? And I can, even from what I mentioned before, I've done a little bit of triage immediately. I can sort of see some functions and okay, well, I think what's happening is that this input fill queue function that's reading stuff from the guest, I'm guessing, it's calling this input batch processing and queue function, and that one seems to be doing some freeing, and then input fill queue sort of gets control back again, and it's iterating this linked list, and one of the links is freed, so it crashes, right? I can sort of start to see where this logic might be happening. So I set some breakpoints. WinDebug's awesome. Dynamic analysis is incredibly helpful. And I run my fuzzer again, and I sort of see most of the stuff get hit. But for some reason, the first thing that strikes me is this free actually is not happening, right? There's no free, so there's no use after free. So I've got to figure out, okay, well, how does this code work? How can I force it to free a packet? Because I don't know what I accidentally did in the guest that was causing this to happen. Okay, so back to VMBus again, but this time I'm actually going to figure out what's happening and try and understand not just that high-level diagram, but get a better, newer diagram where I can really understand what's going on inside these host drivers. Unfortunately, there's almost no public documentation. We're sort of really in the inner workings of Hyper-V, which again on the host side is completely proprietary. There's public symbols available, bless Microsoft for providing public symbols for almost all of the code that's in Windows. But it is a closed source driver. And thankfully, though, it does interact with this open source Linux client, so I can kind of get some information there in terms of what's being sent from the guest to the host. So I reverse engineer as much of it as I can. There's not a lot to go on. There's some debug strings, things like that. But function names especially is kind of where I get a lot of the context information. And I'm able to end up with a pretty decent understanding of the packet processing flow. The sort of driver where the crash is happening manages what VMBus calls channel objects. So for each of the different virtual devices and potentially multiple inside the device as well, there's what they call a channel. And a channel is just exactly what it sounds like. It's a channel for communicating between the guest and the host. There's usually one channel for guest-host communication and one for, there's sort of one communication layer for guest to host and one for host to guest, so they aren't sort of writing over each other. But yeah, this driver essentially creates and manages these channel objects, and then also provides an API for the actual storage driver, the actual network driver, to go, hey, if you want to use VMBus to talk to the guest, here's code to set up a channel and to manage it and set some callbacks and stuff like that. And yeah, there's lots of parsing routines. So definitely this is actually an interesting attack surface. I probably should have looked at this before. So if we look at that sort of shared memory diagram again, sort of the central part of VMBus is that these shared memory buffers get mapped as what's called ring buffers. And you can think of a ring buffer as just an array, right? So you've just got an array of items, and you can add to that array. But instead of getting to the end of it and being well, it's full, we need to allocate a new array, with a ring buffer, you kind of just work incrementally. So you get to the end of it, and then you just start adding stuff back at index 0. And so as long as the writer isn't writing way faster than the reader's consuming, like perhaps a certain fuzzer was causing, yeah, it's actually a really efficient mechanism for sending data because you don't have to keep allocating more and then like freeing the old stuff. You can just keep reusing this same buffer. So each VMBus channel allocates 2 ring buffers, one for sort of the guest to write to and the host to read, and one for the host to write to and the guest to read. So this way, you're only writing to one at a time. It just helps with synchronization, makes it more efficient. And again, thankfully, the Linux kernel has a lot of like code in there that's used to send these kind of packets and messages and use these ring buffers. And so I've tried to minimize the amount of code on the slides because I know it's hard to read. But essentially on the left, we've just got like the header for the packets. So like an actual VMBus message, like a packet will always start with this VM packet descriptor. That's kind of the header. There's different types of them. There's some offsets and lengths and stuff. And then on the right, there's an example of one of the types. And this particular type, the VM data GPA direct, contains the GPA's guest physical addresses. So this is where the guest's like, hey, host, I want to send you some information. Like say I want to like read 2,000 bytes of data from a hard disk, from a virtual hard disk, into some buffer, right? It's going to send this packet. And instead of like having just a 2,000 byte buffer in the packet or something like that, it's going to say, hey, here's the virtual, here's the physical addresses, the guest physical addresses I want you to write to. So that's like the GPA data is just a way of kind of like passing a reference, and then on the host side, it can use that reference to find the shared page in physical memory and write to it, and then the guest can just read it out automatically. It doesn't have to like do a bunch of copying, and it's really efficient for sharing like large amounts of data for things like networking and storage, and obviously in the cloud, you want these to go fast. So here's a sort of a diagram of what the input fill queue function was doing. This is all reverse engineered, so if there's anyone from Microsoft, this is probably wrong, like I'm sorry. But yeah, so first it reads the packet header into a register, and I just mentioned this because it's kind of like a cool optimization. You might be thinking like, wow, this shared memory is kind of unsafe, right? Because what if like the host reads something and then like the guest changes it and then the host reads it again and it's different? Well, they avoid that with the packet header. They just read the whole thing into a register and they never read that header again, right? So there's no like time of use bugs that I could find. Maybe there are, but kind of cool. And so it does a check, is the header valid? And if it's not, just freezes everything and it stops. But otherwise, it allocates a buffer from a Lookaside list, get into that a little bit later. It writes the packet header and the packet data into this buffer, and then it adds it to a linked list. So already, as I'm understanding more about this driver, I'm like, okay, cool, this kind of lines up with what I found when I did that initial crash triage, right? There's some kind of linked list structure of presumably guest data, and something was being freed, so like, all right, I think I'm on the right track. And next, there was this input batch processing queue function. So this was the one where I thought like the actual free was happening. And sure enough, there is some logic in there to free. Essentially, the purpose of this this function is to go through that initial list of packets, and for any packets that have these GPAs, these guest physical addresses, it just does some validation. Like, is this kind of like a reasonable address or like a reasonable description of guest's physical memory? And if not, we're going to free the packet. And then we're going to return an error, and everything's going to stop. So that's kind of like, okay, cool. That's like the error condition. If everything's good though, it just adds it to a different linked list. They really love linked lists and passes that back. But this was like, okay, now I understand maybe why that free wasn't happening when I just ran my fuzzer again. Is we've deliberately got to be sending malformed data, and I wasn't trying to do that. It clearly happened, luckily at some point. But that's kind of what I need to do to trigger this crash, right? So now I'm like, cool. I have some understanding of how to reproduce this. I can write some code in the Linux kernel to send a slightly more malformed packet. So it'll get to that point. It'll do the free. Then we'll have this iteration, and we'll have our user after free, and the host will crash. No, it still doesn't work, unfortunately. Yeah. Done all this work, and something's still not happening, right? So the one thing I haven't really looked at much yet is how the freeing happened. There's just this function called input free packet, and I'm like, cool, it frees the packet, right? Well, not quite. So I go into input free packet, and actually it does this check, right? And it's checking, was the packet buffer allocated from something called a Lookaside list? And if it was, it frees it using this special API, and if not, it freezes using this other API. X-free pull with tag is like the default one, right? If you've used like malloc and free and C, in the Windows kernel, you just expect everyone to use like X allocate pull with tag and X-free pull with tag. That's what I was expecting. But it seems for some reason, like instead, we're not hitting that code path. And again, I set a breakpoint, like can I actually hit this piece of code that I think is doing the freeing, right? X-free pull tag, and I just never see it. I spent quite a bit of time going down this rabbit hole. I'm just never able to get that particular piece of code to execute. And eventually, I kind of just submit to the fact that I'm going to have to understand even more and dive even deeper into what is an n-page lookaside list, and like, is there a way to cause this to cause a free? The Lookaside list API is documented, and you don't have to read all that. Essentially, a Lookaside list is like a caching allocator. So what that means is you go to allocate some memory from the operating system, you use it for a bit, and then you free it, right? But if you're allocating a lot of stuff and then freeing a lot of stuff, this can get pretty inefficient and like expensive in terms of constantly having to go to the OS allocator and be like, give me more memory, here's it back, give me more memory. And so what the Lookaside list does is you allocate a bunch of memory, and it will just when you free it, it'll just hold on to it. It won't actually go back to the OS and say, I'm just going to hold on to it for a bit, because I know that you're probably going to come back to me soon asking for more memory, and I'm just going to give you the stuff you'd already allocated, but you thought you'd freed. So that's kind of why I'm not seeing this crashing condition again, is because what's actually happening is we're just freeing it back to this Lookaside, and it's never really being freed. Like nothing else is able to use that memory, and so that's kind of like blocking us from having like we know the crash can occur. We've got this crash dump we stumbled upon, but we can't get it to trigger again because this Lookaside list is kind of blocking us. And it's unfortunately not very well documented, like in terms of how it works internally. Like there's nowhere in the documentation like, oh yeah, if you just want to get one packet to go back to the OS, just do this thing. And so I was like, all right, well I have to understand how the Lookaside list structure really works and dive a bit deeper into that to get a better understanding of how to force like one specific packet to be freed so I can actually cause a use after free, reclaim the memory with something else if I want to. And so, yeah, again, a little bit of code. This is the rough structure of the Lookaside list that I was able to reverse engineer a bit. It's not documented, but a bunch of people like React OS have got some definitions. I found the one in the version of the kernel I was working on to be a little bit different, but they were pretty close and definitely a good starting point. And the three main things I realized you sort of have to learn about a Lookaside list is the list header. So it's essentially a singly linked list, so just like a list of allocations. As you allocate memory from the OS, it just puts them in this big list. And then these two other fields, the depth and the maximum depth. And this definitely took me a while to kind of get my head around it. It wasn't explained well on the developer documentation. But the depth is essentially like the number of freed packets that we're holding onto, right? So we allocate like 10 packets, and then we free 10. There's the max depth says, oh, we can only hold on to 4 of them, but we'll hold on to those 4. So if you need to allocate again, we've got up to 4 available before we have to start going back to the OS. My partner's an amazing designer, and she's very kindly made some animations that hopefully will make this like a little bit clearer about what's going on. Cool. Yeah, so allocate from the OS. They go into this list, there's like the control structure, and then we free them, and they don't go back to the OS, right? We hold on to them, and then we can just use them again, right? So pretty simple, pretty cool. Trying to get it to the next one. Cool. Okay, cool. But what happens if we allocate like more than we need and more than this max depth figure, right? Well, so we allocate a bunch, but as soon as we try to free more than 4, right? Because 4 is our max depth, then that one goes back to the OS. So I can just run that one through again. Like we allocate, in this case, 8 blocks of memory with the Lookaside list. They go into this list, and then if we free them, if we free more than 4, which is our max depth, then we can get it back. And so I'm like, okay, cool. I finally sort of understand how we can get the Lookaside list to free a piece of memory back to the OS, and then we could reclaim it and have like a use after free condition where the driver is using memory that it thinks is of one type, but we've actually like it's been freed and we've replaced it with a different type, and maybe we can get some exploitability, like an exploitable bug out of that. So sorry, just trying to get cool. So like this is kind of where we're at. And I've got some idea of how to get this to happen, but I'm not really sure how to like make this happen in terms of like using this Lookaside list. Like in theory, I now understand like, okay, so I need the max depth. In this case, 4 was the real number, right? It would hold up to 4 of these packets in the list before it started sending them back and go, okay, we're not going to hold on to like 100 packets. But I need to perform like an extra step. And so I was like, all right, how can I make this happen, right? So I'm thinking about the packet passing flow. I read some data from that the guest's written to me, like as the host. And assuming the packet head is valid, I then go to this Lookaside list and I allocate a buffer. And I'm like, okay, so this buffer contains a valid packet. I'm going to add it to a linked list. And then once that first linked list is full, I'm going to pass it to this other function. And this function is going to check that if there's any guest addresses in there, they're also valid, and that's all good. And if it finds any that are bad, it's going to free them. Or it's going to free the first bad one it finds and then stop. So we want that first bad one to actually be the one that Lookaside list goes, yeah, no, I don't want that one. I can't hold anymore. Send it back to the OS. And there's just kind of a fundamental issue with the way the Lookaside list works in terms of thinking it as a state machine, which is that every time we allocate a packet from this buffer, we reduce the depth, right? Depth is how many unused things do we have. And so if we use one of them, well, the depth goes down. And so just kind of the act of allocating this packet, if I send a bad packet, that's dropping the depth, and then it goes to free the bad packet, and the depth just goes back up to 4, even if it was at 4 before. So I was I'm so close, but just something isn't quite working. And it took me a little while of thinking about this to be how can I get this packet to be freed back to the OS, right? I know it can happen. I've got this crash. And if you've sort of done a lot of VR before, you might have some idea of there's still one thing I haven't really talked about or looked at. And that's how does a good packet get freed? That's kind of the missing piece of the puzzle that I ended up on. So I set what's called a hardware breakpoint on just a regular packet. I was okay, a hardware breakpoint is a regular breakpoint you may have used in your code. You're hey, when this bit of code runs, I want you to stop and tell me we've hit this. But a hardware breakpoint, you can actually say when this bit of memory is accessed, I want you to stop and tell me. So I set a hardware breakpoint on one of these regular packets. I hadn't messed with it. It's all right, what's the lifetime of a packet? Where does it go? Where does it end up? And I got this huge call stack. Again, you don't have to look at the whole thing. But it ends up in this VMB CMR, it ends up in a packet completion function. That's hey, we've finished using this packet. We don't need it anymore. And that's where it gets freed. And the interesting thing about this call stack that I found, though, was there's none of the other VMBus code in here that we've been looking at, right? So it's actually a completely different call stack, and it's happening in a completely different thread. And this was kind of the key to this puzzle was actually, we can have packets being freed in one thread while they're still being allocated in the other. Finally, things are starting to make sense. And so I had a plan, right? This was finally coming together. We spray some number of good packets, so the number ended up being about 50. We wait just a bit of time for the packets to start to get processed and then completed, right? And so when they're completed, they get freed, and so that Lookaside list is going to start having a bunch of free slots, right? We've finished using the memory. Well, we're not going to give it back yet because we're a Lookaside list, but if we have enough of them free, then actually they will start going to the OS. And so if I could line up the timing so that a bad packet gets allocated kind of while the other packets in a different thread are being freed, the bad packet will drop the depth, right? Because it's hey, I'll use one of those slots. I need some memory. Then I can pad it with some larger packets. So the other thing is these channels had I think they had 10 Lookaside lists of different sizes. And so if you sent a radically different sized packet, it would go from a different Lookaside list. So it's not messing with our little bad packet Lookaside list state machine. And then hopefully while the packets are still being processed in our sort of input thread, off in the other worker thread, the packets are still being freed and try and just get the mathematics to line up so that the packet gets allocated and then another one gets freed somewhere else. And so we can bump that depth up to 4. And eventually, we can actually have our packet get freed for real back to the OS, and we can have our use after free condition. And so it's kind of this was the bit where I was okay, I finally understand enough about this whole process to get it to actually crash. And again, hopefully a nice little animation to kind of explain a bit more about what's happening. So it's fill up a bunch of good packets, send it down to a network device, the network device thread, which does the main processing. And then here, so the yellow packets are just a different size, right? So they don't interact with the Lookaside list that the green and red do. They're just kind of padding. But here you can see while this thread is sort of processing and freeing these regular packets, we send out one bad packet. The depth goes down to 3, but then they keep processing, right? And they free a few more. And so finally, we're able to get this bad packet to be freed actually back to the OS and cause a use after free. This was kind of after all this work, finally understanding the like 4 or 5 different components I needed to bring together to get this to happen. Again, trying to exit this video is interesting. Okay, cool. So yeah, the final steps were to write the code in the Linux kernel to just spray a bunch of regular packets. So I used the networking driver actually for this to just send a bunch of packets like, hey, I want to set the MAC address, and they just went off and did this. Then send one malformed packet, which required a bit of tinkering because there wasn't really code to send malformed packets in the kernel for some reason. I don't know why they don't provide that as a feature. Play with a bit of timing to try and like have a little bit of a delay because you need to, all this happens asynchronously and you sort of need that worker thread to be going in the background by the time the bad packet comes. And then finally put it all together, and I got a crash. Like I got it working. I was able to reproduce it, not just once, but like repeatedly. And yeah, write up the report. Thankfully, we'd done all this work to like understand how this worked, so it was a really good report, and I could explain the root cause really well, and send it off to MSRC and get some sleep. Basically, everything from like finding the crash to this point was like 10 days of a lot of work. Like I was kind of obsessed. So yeah, that was a really good feeling. And yeah, after a few months, got probably the best email I've ever got in my life. And like serious props to MSRC because they really put their money, the money where their mouth is. I know a lot of bounty vendors. I haven't worked with them, but I hear some rough things about other places. So yeah, like incredibly cool, especially after putting in all that work. I can only imagine if they'd come back and be like, yeah, we're not really interested. So very cool. And I'm sure some of you are like, well, is it exploitable? We'll get to that in a second. Not as much, but basically MSRC was happy that like there was enough potential that they were willing to pay out the full amount. So sort of looking back at some of the lessons learned so far. So we've covered a lot of stuff. So we've learned about Hyper-V, sort of like choosing one target, having this great idea of like where I think the research is going to go and like how it's all going to work, and my awesome fuzzer, getting a bit sidetracked, but then yeah, like getting this crash, right, and just sort of being persistent, working through it, and really understanding what was going on. Like the real key to it was when I initially started this research, right, I just skimmed over some things, and it turned out like actually learning about it and not just trying to automate everything was really pivotal to actually being able to reproduce it and turn it into something cool. And yeah, modeling the Lookaside list state machine was something I was definitely not expecting to do at the start of the project. And hey, we ended up with a cool proof of concept that we could send to Microsoft. Exploitability. Look, in all honesty, I think this would definitely not be the bug I was going to choose if I was trying to write an exploit. Very small window to like reuse the site after it had been freed, because it's essentially just like iterating a linked list. And we can pad the linked list with those other size packets, but we don't have a lot of time. The proof of concept worked about 30% of the time. If it didn't work, all you had to do was restart the guest VM, right? So if you think about Azure, like you can do that as many times as you want. Like it's not really an impediment. But once you've caused the use after free, if you like fail to put something else in there, it may end up getting captured by a different free, and like that could cause a crash. And the use after free was just a read. So I spent a bit of time trying to see if maybe there was somewhere else in the code where maybe like, it would try and, there was some function pointers in this object, like does it call a function pointer, or like maybe do some kind of write based on it. From what I could tell, it was just a read. But I'd previously reported stuff like this just as a DOS, and Microsoft had like upped it and like given it a higher rating. So I was like, I'm gonna say it's RCE, and they agreed. So that was kind of cool. They added me to an old CV retroactively for some reason. But the old CV was found by Peter Hlavity, so I guess I did a good job like replicating his work, right? Because I essentially just found a variant of that. So in terms of the actual lessons learned, I think the big one for me was like, research is fundamentally about understanding. And I got a little bit sidetracked at one point with like, hey, like Rust is fun. I like writing it. It was really cool. But also like just coming back to that understanding and like, I did get lucky, and like, yeah, like just trying stuff and getting lucky isn't something you can really replicate. But what I can replicate is like, if I get a bit sidetracked, just remembering like, am I actually understanding this, or am I just like writing code for the sake of it? Multi-threading increases complexity so much. I think it's really easy to underestimate that. Just like that Lookaside list state meant that we sort of in like a single-threaded model, we wouldn't have been able to get this crash or to make it exploitable. Like technically, at like an academic level, the use after free was always there, right? The Lookaside list was always going to mark that buffer as freed, but because of the way Lookaside lists work, we couldn't really put like a different type in there. Like it wasn't useful at all until multi-threading came in. The Lookaside list object was being shared across threads without any synchronization. And so suddenly like we're able to get some behavior that perhaps wasn't intended. Again, it's a non-default allocator, right? So it's going to also hide things like special pool that are supposed to find these kind of use after free bugs. And transport layers matter, right? So it's easy to be like, oh, I'm working on this cool thing. It's over TCP. Like, there's no bugs in TCP, right? Well, no, people are still finding bugs in TCP. And in this case, yeah, I was like, oh, VMBus is just like the transport layer, right? It's not like a thing I have to care about. All the cool stuff's up in the device drivers. But actually, it turned out to be a really interesting attack surface. And even if it wasn't, right, I actually needed to learn about it just if I wanted to use it for sending those packets. And yeah, variant analysis is awesome. There's been some really cool talks. Maddie Stone actually gave a talk a few years ago about variant analysis, where she gave a bunch of really cool examples of people don't patch things properly. But it doesn't just have to be oh, I'm going to recreate this bug that someone else found. It could also be oh, this person had a really cool idea, and I'm going to re-implement that idea in my own way. And the advantage of that is you're almost certainly going to do some things differently, and so hopefully you'll trigger some code paths that they haven't, and find some cool bugs that way. Yeah, good tooling is invaluable, but don't overcommit to tooling before you've kind of confirmed that it's going to work the way you think. And when it comes down to it, we've got to be persistent. So some shout outs to these guys who helped me with the reporting process and also reviewing the CFP, and everyone who gives this kind of research, right? I learned so much from reading and watching presentations that people have given of their research. So hopefully you got something out of this one, and a big shout out to everyone who does sort of present publicly. Yeah, any questions? Thanks.
Do we have any questions in the audience?
It's fine, it's lunchtime, I'm not offended.
There's one just in the middle over on the right.
Hello.
Hey.
Thanks for sharing great insights. It's fascinating how we came from open source is a cancer to how Windows and Linux are now interlocked, integrated. So the question was in the process of understanding of both. You mentioned you reverse engineered some Windows stuff. You spent time in Linux kernel. What did you use for reverse engineering in Windows space, and to what degree you had to have decent understanding of source code and Linux kernel for research similar like yours? Thanks.
Yeah. So on the Windows side, so I like Binary Ninja, but honestly, I think whatever tool works best for you. So when I started doing this stuff, it was when Ghidra came out, because it became accessible, and that was really cool. It's a little bit of an eyesore, I think, but really whatever works for you. I think Binary Ninja is awesome if you are wanting to pay a bit of money, but not IDA money. I don't have IDA money. So Binary Ninja is great, and that's what I use for all my reverse engineering now, just because once you commit to one tool, you can write some scripts and stuff. On the Linux kernel side, I did have to spend, when I was triaging, why is my Fuzzer crashing its own kernel? I spent quite a bit of time reading that. And that was certainly helpful in terms of when I then went to write the proof of concept, I did actually have some understanding of okay, so VMBus has got these ring buffers and it's got some queues, and here are the functions that already exist in the Linux kernel source that I can leverage to write that stuff. So yeah, that was mostly useful in terms of reproducing the proof of concept. But as I did show, having the some of the type definitions for data that was being sent from the guest to host was also really useful when on the host side there's no documentation, and I'm in this huge function in Binary Ninja. I'm where do I even start? Well, I can see this is coming from the ring buffer, and I can open WinDbug and oh yeah, this is a packet I've sent, and I can kind of map that structure into Binary Ninja and start to understand what the structure definitions were and work outwards from that. Any other questions?
Hello. Thank you for the talk. Before, when you were mentioning how the freed packet goes to the Lookaside, the second array, and then that gets freed and goes to the kernel. You said that it gets freed in the first place from the first list, and then it gets repurposed to the second, and then freed there, and that's when it goes back to the kernel. So the question is, why does this end up being a use after free and not a double free vulnerability?
So it was being, so it goes to the worker thread. The worker thread, the graphic might have been a little bit confusing. So essentially, what was shared between those two was the Lookaside list that was kind of backing the memory. So the worker thread finished using a packet and it freed it. And so, but what really happened is the Lookaside list just marked that as free. And then so when the bad packet was then allocated a bit later, it was allocated from that same Lookaside list. And so the Lookaside list just reused memory that was never really free, right? It never really went back to the OS. It just like used that same slot. And then when the bad packet was detected, that's when like the real free happened. So I guess it wasn't a double free because we're not like, I don't know, I definitely think it's more like just a use after. I think like maybe depending on how like the semantics of the Lookaside list, you could classify it as a double free. But from my perspective, it was more of like the packet was like the packet slot was supposed to be reused because that's how the Lookaside list works, right? It's caching these buffers and then it's just kind of like providing them to whatever driver is using them for reuse. But I always just thought of it as a use after free. Maybe there's an argument that it's actually a double free. Certainly in terms of like how it's being used, is that it's like there is a memory read. It's actually like a memory compare of a value inside this location that has been freed. So like when I did play with like trying to replace that buffer with other allocations, it was just like a use after free read that was essentially occurring.
There's a question right up at the front, just over there.
You mentioned that this same sort of architecture is used in Azure. Have you tested it in Azure? Does it work?
No. So in fact, basically, as far as I'm aware, an identical architecture. Like Hyper-V is what's used underneath Azure. There's probably like a slightly different version of these drivers that's used there. They do not like you testing this stuff because, again, like even if you DOS Azure, like that's a big deal. They don't like that. But from my understanding, like if you look at the bounty page, and you can actually get some like Azure-like versions. Like you can get Azure on-prem now. And I've looked at those binaries and they're very, very similar. So I think the behavior of some of the particulars might be a little different for like obviously scaling purposes, but all of the mechanisms to my knowledge are basically identical. That's one of the reasons I think Hyper-V is kind of the only cloud hypervisor you can really target in this way for bug bounty. Like they offer a GCP and an AWS bounty, but like I don't know which custom version of KVM they're using. Like I could look at the KVM source, but I'm sure they would have forked it and changed it, and so it'd be way harder to find a bug in KVM and go, hey, give me some bounty money, because they'd probably come back and go, oh, we don't even use this bit of the code, or like we've already fixed that upstream on our version, so yeah.
Are there any other questions in the audience? I'll look around. We have a speaker gift for you that's out backstage. Let's thank Leo one more time for an amazing presentation.